Warm welcome to the lecture of Analog Integrated Circuits Design. This is lecture number 2, Unit 2. And we started the discussion on operational amplifiers. And in yesterday's class, we saw that there are three main topologies what we'll be looking at. One stage op-amp, two stage op-amp, and one additional technique which we employ to this one stage op-amp to improve or to boost the gain of the structures. So in today's class, we will start with telescopic op-amp. So before we go to telescopic op-amp, let us start a discussion with a very basic structure, which is nothing but a differential amplifier. So, so I request all of you to draw and write the gain expressions when I'm doing along with me, because if you just see what I'm doing, you may think that the circuits are big, but if you draw and understand along with me, then it will be easy for you guys. All right. So when you talk about single stage op-amp or one stage op-amp, where there will be only one stage, so the very basic structure is our differential amplifier, what we have discussed in unit 1 at the end, with a current mirror load or an active differential amplifier. So I'll draw the structure here. So this is the load devices, and you know that there will be a connection like this here, and here we have the input transistors followed by the tail current source. So it is common to mark the inputs like this to show that this is the differential input, and this is single ended output, so we mark it as V out. We can number this as M1, M2, M3 and M4, and this is VDD, and there is a tail current source of value, say some I0 or ISS, whatever notation we can give. So this what you are seeing on screen now is differential amplifier, but this is also considered as an operational amplifier, as I think the same thing was discussed some other day. So this is a high gain, if this is a high gain differential amplifier, definitely this can also be considered as an op-amp. Now, looking at the circuit, can I know what is the gain of this circuit? Anup, can you help me? Can you tell me what is the gain of the circuit? Anup.
Yes, sir.
Yeah. Can you tell me what is the gain expression? AV.
Minus GM1
Mm-hmm.
R0 3 parallel with 1 by GM3 parallel with
Mm-hmm.
R0 1.
Yeah, but you see, output is on the other side, right? Your output terminal is here. So we have derived how to get the gain expression of this. It is not on this side. So maybe you have directly applied half circuit analysis, but half circuit is not possible here. Even though the result is same as half circuit analysis, that we cannot do half circuit analysis because the circuit is not symmetric. But the expression will come as minus GM of 1 or 2 into R0 2 parallel to R0 4. We cannot write it as R0 1 parallel to 1 by GM3 parallel to R0 3, because that is not the side where we are taking the output. Is that clear, Anup?
Yes, sir.
Okay, yeah, thank you. So now whatever you are seeing now is single-ended op-amp, and this can be shown like this as minus plus, and this is the single-ended output. Right. Now, if you go for the differential version, fully differential version of this, can you tell me what change I should make here to make this fully differential? Anyone? Can I get your response in the chat box? So what change I should make to make this circuit a differential one? Remove current mirror configuration. So what do you mean by that? You meant that I should remove this connection?
Sir, I'm the bridge between M3 and M4.
These two. And what should I do?
And the other side will be the negative differential output.
Yeah, that is true, but by how we need to bias this? M3 and M4 also need to be biased, right? Yeah, that is true. Whatever you're telling is right. We have take output from here, and this connection can remain here because we will apply a common bias voltage here that will bias both M3 and M4. Now, how can we say this is fully differential? Because we know that when you say differential, those points should have equal and opposite signal excursion. Along with that, those points should have equal impedance, right? So if I have a connection like this, what you are seeing here, and if I try to take output from this point with respect to this point, both points do not have equal impedance, because one side the impedance is 1 by GM3 parallel to R03, which is small, and on the other side you have R04. So directly taking differential output from this point is not right, also not correct also. But when you come to this side, if I remove the diode connected structure, what I am getting is two MOSFETs, both are current source load, and by biasing that properly in saturation, you can definitely get output voltage here. So I'll mark this as Vout1 and this as Vout2. All right. So if at all supply, so the here it is raining heavily. So by any chance, if my internet connection is getting disconnected, I'll please wait. I'll come back. I'll connect it using my mobile data. All right. So now in this case, can you tell me what will be the gain? What will be the gain in this case? Can I get your response in the chat box?
Minus GM1 into R0 1 parallel R0 3.
R0, yes, R0 1 parallel R0 3, or we can write R0 2 parallel to R0 4, because now Anup, as you told before, now this is a fully differential circuit with with symmetrical circuit. So you can do half circuit analysis, and your the gain can be written as minus GM of 1 or 2 into R0 1 or 2 parallel to R0 3 or 4. This can be the gain expression, right? But it is right if you write for one side R0 2 parallel R0 4 if you write, or the other side if you write, both are fine. And if you see the symbol of this, we will mark like this as plus and this as minus. So this is fully differential. So the first one is, this is single-ended, and the second one is fully differential. Right. Now, what is one main difference between both the circuits? It is giving you the same gain, but what is another difference? Or are there any difference in the output what we are getting from these two? Any response?
No, sir. No difference.
No difference. Yeah, but there is one difference, because your second circuit is fully differential. Your output swing will be doubled. That is the inherent advantage of a differential circuit. All right. What I told here is, in this case I'll be measuring output here with respect to ground. With respect to ground I'll be measuring, but here I'll be measuring from here and here. So the inherently you will have a double output swing. All right. So now we will quickly see one question. So I'll write on the question here. We know what is ICMR, especially for the previous circuit. So the question is to calculate the ICMR, which is input common mode range of a unity gain buffer, it is given that the supply voltage VDD is equal to 3 volt, overdrive voltage is equal to 0.3, 0.3 volt, and VT is equal to 0.7. Yeah. So the question is to calculate ICMR of a unity gain buffer with these things given. And if you wonder what is an unity gain buffer, if you have an op-amp of this, unity gain buffer is nothing but a voltage follower. So if you connect output back to the negative of the input, we can think of this as a voltage unity gain buffer or a voltage follower. All right, now the question is calculate the ICMR value. So any hint of how to start this? All right, so how will you say this is a unity gain buffer? Yeah, by checking the gain, you can see that op-amp, this is a negative, negative feedback. And when in negative feedback, we know that the voltage at the inverting terminal is equal to voltage at the non-inverting terminal, and with that I can say V in is exactly equal to V out. So this will definitely act as a unity gain buffer. Now the question is, what is input common mode range? Now here how we should analyze this, we should replace the op-amp with its proper equivalent. So based on the architectures we discussed, we have only two architectures. So which one we will choose? We can choose this architecture over there because this is the single-ended configuration. So here you have single-ended op-amp. So bring that circuit here and do slight modification, and then you can find the ICMR or the input common mode range here. So this is the circuit, and how I should modify the circuit is this should be connected here, and this is V out and this is V in. All right, so can you calculate what is ICMR now? Can I get some response? So what is ICMR? Input common mode range. So when we say it is a range, we have two values. One is ICMR minus and another one is ICMR plus. Right. So what is ICMR minus? Aritra, can you help me? How to find ICMR minus?
So 1 minute, sir, thinking.
Yeah, looking at the circuit diagram, only you should say.
So I'm not sure, sir.
Okay, what is ICMR?
So a common mode rejection, sir.
Oh, common mode rejection. Okay, all right. Yeah. So it is not common mode rejection. It is input common mode range. So I think you are
Yes, sir.
not
Sorry,
following
sir.
classes for some time. Yeah, that's okay. Anyone else? How will you find this ICMR minus? Bhuvan? Oh yeah, I think people have written answer here VT1. It is not VT1. Vaishnavi, yes. Yeah. So so what do you mean by ICMR minus? ICMR minus is the minimum voltage that is required at the input side. So input side is here. The minimum voltage that should be applied here such that the transistors should be in saturation, right? So if you look at here, now you can see that I naught is a current source, but how will you mm, like realize I naught that is using another transistor? So that transistor should be in saturation. That means there should be a drop here, or there should be a drop across the current source. So as of now, I will say that drop across the current source is same as, so when you think in the practical way, you will realize this current source using a transistor. The transistor should be in saturation. If in saturation, that drop should be equal to VOV, overdrive voltage of that device, right? And now that is equal to the voltage drop across the current source, plus this transistor also need voltage to be turned on. That should be the VGS voltage of that particular device. So the minimum voltage that is required here is equal to VGS1 plus the voltage drop across the current source. That could be the overdrive voltage of that, right? Now how will I write this? There are only two things given: overdrive voltage is given and threshold is given, and this can be used for all the devices. So what is overdrive voltage? Overdrive voltage is nothing but VGS minus VT. That is given as 0.3. So what is VGS? VGS is equal to 0.3 plus 0.7, which is equal to 1 volt. Right. So how will I calculate ICMR minus? ICMR minus is equal to VGS1 is equal to 1 volt plus voltage drop across the current source is same as overdrive voltage, which is equal to 0.3, which is equal to 1.3 volt is the ICMR minus value. Right. Now what is ICMR plus value? So ICMR plus is so ICMR plus is the maximum voltage what I can apply here, maximum voltage that can be given to the gate voltage. So what will be the maximum voltage which I can apply to the gate of this transistor M1? Any idea? Dhananjay,
Yes,
are
sir.
you there, Dhananjay? Yeah. Yeah. Can you tell me what can be the maximum gate voltage I can give to this MOSFET M1 to maintain it in saturation?
Sir, I don't know, sir.
All right. So Arun,
Yes, sir.
yeah, what is the maximum gate voltage I can apply to this?
So I'm not sure, but not sure, sir.
All right. So who can tell the answer for this? See, my question is very simple. You have a MOSFET. You have a MOSFET. Say you know this node voltage as Vx. Now, what can be the voltage? What can be the maximum voltage I can apply to the gate such that the transistor remain in saturation? Yes. Yes, Bhavya. Yeah, a lot of answers are there. Right. Yeah. So the answer is your gate voltage can go maximum of one threshold higher than the drain. That is what our condition for saturation, right? Condition for saturation is VD should be equal to VG minus VT. So what the gate voltage can go? It can go maximum up to one threshold higher than drain. That is a very simple logic behind this. So now for ICMR plus, When I write the maximum voltage that can be given to this gate, it is equal to this node voltage. Say this is Vx. If that is Vx, I can say that is equal to Vx plus Vt. Right. Now we should write what is Vx. What is Vx in this case? Vx is this node voltage. So if you look at the DC voltage at this node, this is VDD, and from VDD you have to subtract. This is minus, so this is plus minus. I'll write this as VSG. So Vx is VDD minus VSG. All right. So your ICMR plus is equal to VDD minus VSG plus VT. This is your ICMR plus VDD minus VSG plus VT. Or this can be further written as VDD minus this VSG minus VT, which is nothing but the overdrive of a PMOS device. So that can be written as 3 minus 1 overdrive, which is 0.3. So your ICMR plus is equal to 2.7. Is this clear? Yeah, I saw the answers. I think Bhuvan, it is not Vx minus Vt, it is Vx plus Vt. And yeah, so everywhere I have, so I have taken Vt, like mode value of Vt only I have taken, because it is for the top device it is PMOS. So Vt equal to 0.7 means mode Vt, like plus or minus it is 0.7 value is what I meant there. All right, so if you have any question on this, please ask. Otherwise, we'll move forward. So this is a very simple way how we can analyze a unity gain buffer to find the input common mode range.
Sir, VGS minus VT and VSG minus both same?
Yeah, so if you remember, for a PMOS device, when you talk about overdrive voltage, it is VSG minus VT, or you can write in terms of VGS, then we have to accommodate the minus sign, because you see, for a PMOS device, source is at a higher potential than gate. So VSG will be positive always.
Oh, yes, sir. Got it.
Yeah, yeah. All right. So in the same line, now I'll introduce the new structure, what we mentioned before as telescopic Opamp. So the root structure is same as this. This is the root structure. So here, if you identify the devices, these two M1 and M2 forms the basic input pair, and M3 and M4 is actually load, and load here is a current mirror load. For current mirror only I am writing it as CM. The load here is current mirror load, right? Now the basic idea behind telescopic op-amp is, we know the gain available for this circuit, right? The gain available for this circuit, if I write the AV expression, it is equal to minus GM GM of 1 comma 2 into R02 parallel to R04. Now the question comes, we are talking about cases where we need a open loop gain very high value. So when you think about high value open loop gain, what is the possibility, or how you can improve the gain of this current structure? Any suggestions on this? So you know the gain equation. So if you want to increase gain of this structure, what is possible? So what technique I can use and how I will use that? What are the possibilities of increasing gain of this structure? Can I get some response in the chat box? Add more transistors to the load. Okay, so adding more transistors in the sense how it will help in increasing the gain. Yes, cascoding, very good. Yes, cascoding is what we can do and at one stretch. So by cascoding, what we are doing here, by cascoding we are trying to improve the impedance R02 and R04. So if I can increase the impedance R02 and R04 proportionately, the parallel combination also will have a significant increase, right? So in that line, what we will do is, I'm just taking the structure here, and now I will think how I can employ cascoding, right? So how will I employ cascoding here? So this is the load part. This I removed to that, to the top. So this is my initial structure. I have just removed the load and kept it here. So why I did this here is because now you can see that yes Anushka, that is right. It'll increase by GMR0 value. So now you have M1 M2 devices, M3 M4 devices. You are trying to increase the output resistance of the transistors R02 and R04, but you cannot do just you cannot do only on one side, because when you employ that you have to see the biasing of that devices also. So, and to have a uniform and symmetrical structure, we will employ cascoding on both the branches. So you have devices M1 and M2. So the very first thing what we will do here is we will add cascode transistors for this M1 and M2. So listen very carefully. We will add cascode transistors for M1 and M2. So how will I add? I will add in this form. So cascoding, since it is cascoding, I will use the same device. If it is folded cascoding, I will use a different device. So these are the two devices I have added here. And this is basically to cascode or to increase the output impedance of M1 and M2. That means previously the output was taken with, okay, we'll talk about output a little later. And this need to be biased. So I am just marking it to a bias point. Similarly, if you look at the load M3 and M4, that also need to be cascoded. So now the load is a current mirror load. So the cascode is also suitable for a current mirror load. So how will I do that cascoding? Is by extending the structure in this form. Since it is a current mirror load, this is also connected. And now output will be taken from this point. This is the output point. All right. So how will I number this now? So for the in order to keep the same number as before, if I keep this as M1, M2 and this as M3 and M4, these numbers can be put as M5, M6, and this can be taken as M7 and M8. Right. So how will I identify each structure? This is input pair. M1 and M2 form the input differential pair. This is actually M3 and M4 is the initial or the actual load. Now M5 and M6 are cascode for the input pair, and M7 and M8 are cascode for the current mirror load. So this is the new structure. Sorry. And so what we have done here is we have increased the gain of the structure. We will see shortly how it will become how the gain is increased. So we have increased the gain of the structure by extending the structure, right? So previously it was only M1, M2 and M3 and M4, but we extended the structure by adding transistors in between, and thereby we increase the gain. That is why we call this op-amp as telescopic op-amp, because we know in a telescope, to see the objects at a far distance or to use the telescope properly, we will actually extend the structure of the telescope, right? It is in a similar manner. Here it is not in a similar manner, but we also extend the structure to have more gain. So increase gain by extending the structure, or basically by cascoding, by extending the structure, that is by cascoding, and hence we call this as telescopic op-amp. Is that clear? So this is your telescopic op-amp. Any questions on this? So if you see this circuit diagram directly, you will think that, oh, this is a big circuit diagram, but if you understand it properly, that is why I have just used two colors. The navy blue color shows the initial circuit, and between the pink color is what I have extended the structure by adding the cascode devices for both load and for input devices. Are there any doubts in this? Can I get your response in the chat box? Can I get some response? All right, no doubts. Okay. So since we have drawn the structure, now the next step is actually to find the voltage gain of this structure, voltage gain. So how will I find voltage gain? Voltage gain is generally found by writing this expression of Gm and Rout. That is how we write, we find voltage gain, right? So okay, so you guys can try to find Gm and Rout separately for the structure. Meanwhile, I'll just check with Anirudh. So okay, Ananya Sharma. Ananya, are you there? Ananya. Okay, Ananya is not there. Anirudh. Anirudh R.
Yes, sir. Yes, sir.
Yeah, Anirudh, can you tell me what we did with this telescopic op-amp, or what is your understanding on this telescopic op-amp?
Sir, I just came now, sir. I got disconnected, sir.
Oh, isn't it?
Yes, sir.
Is it? So I didn't see. You just came now, means you were not there from the beginning of the class?
No, sir. 5 minutes, 5 to 6 minutes, I got disconnected, sir.
Okay, so till what you heard?
Till that AV is equal to that left side, sir.
All right. Okay. Okay. So you were there for this, right? This structure.
Yes, sir.
Okay. So you understood how we calculated ICMR plus?
Yes, sir. Yes, sir.
Yeah. Can you tell me how did we calculate ICMR plus for the previous question?
Sir, could you go back to the previous slide?
And the same thing, the same circuit diagram. You can see the same circuit here also, right? How will you get ICMR plus for the circuit? Yes, Anirudh, any response from your side?
Yeah, sir. One minute.
No, you can just look at the circuit diagram and you can tell me. No idea?
Yeah. So, could you explain once more? Right?
So you were there, you listened to the class or not?
Sir, I couldn't, like, I had issues with the network, so, sir.
All right. So Ananya, are you there? Ananya?
Yes, sir.
Yeah. Ananya, can you tell me what you understood about this telescopic op-amp?
So we are basically using the property of cascading in order to increase the output impedance and hence increasing the gain.
Okay. So, so why this is so? Can you tell me what is the gain of the circuit, or how the gain will be improved by this extending the architecture? Any response, Ananya?
Yes, sir. By the cascading property itself, we are increasing the output impedance.
That is
And
what cascading property means. What? How it will improve?
by stacking up the transistors.
Understood. So, like how much will be the improvement in the gain? So, were you listening to the class?
Yes, sir.
No, I called you before, then you didn't respond.
Yes, sir. My mic did not work, I think.
Oh, is it? Okay. Okay. In that case, you can use the chat box to respond.
Yes, sir.
All right. So you do not know what will be the improvement here?
So the output gain will increase by GMR naught.
Output gain. Output gain.
Output impedance, sir.
Yeah. How it is improved by GMR naught? So tell me. So in the first circuit, it is R naught, R naught 2, right? Now, how it will be improved? Which transistors GMR naught will get improved? Yeah,
Sir,
quick,
M2
Ananya.
and M4.
M2 and M4. Yeah, so M2 will be improved by how much? What will be the amount, and which transistor will improve M2's output impedance? Uh, yeah, please, quick.
So like M2 will be increased by M6.
Okay, all right, okay. Yeah, so what we will do now is, yeah, thank you, Ananya. Yeah. So what we'll do is, we'll find the gain. Gain is equal to GM into R out. So we'll take the same structure and we'll find GM and R out separately. So you guys can try, and if you're getting the answer, please share in the chat box and I'll tell you how to calculate this. Yeah, this is a circuit. So how will you calculate the GM of the circuit? So let us see that first. So AV is equal to GM into R out. Okay, Aryan,
Yes, sir.
yeah, Aryan, can you tell me how will you find the GM of the circuit?
Uh, yes, sir. Yeah, short
Yeah.
the output to ground and yeah,
Mm-hmm.
consider the short circuit current by considering the short
Very
circuit
good.
current.
Thank you. Yeah.
Okay.
Thank you, Aryan. Yeah, that is right. So we will short the output to ground, and I'll take a current here, and I'll mark it as I out. Right. Now, if I can find what is I out by VID, that is my short circuit transconductance or GM. Right. So if you remember, I told that when the number of transistors when it increase, we will not replace the circuit with its equivalent by drawing the small signal equivalent circuit of the transistors. Rather, we will find the GM pictorially using the same circuit diagram. So that is what we will do even here also, because if you try to draw the equivalent circuit of this, it will be very difficult because there are almost 8 transistors here, right? No, 9 transistors, including the I naught transistor. Now, how will you find GM? So VID is the current. So this transistor will have, sorry, VID is the voltage, differential voltage. So M1 will carry a current of GM VID by 2, and M2 will carry a current of minus GM into VID by 2. The same way what we have done for the differential amplifier, right? So this is a current. Now, if M1 is having GM VID by 2 current, so what I'm talking here is a small signal current. So M5 also will have the same current, which is GM VID by 2. Now M6 also will carry the same current because both are same branch, minus VID by 2. All right. Now the current through to M5 is definitely it can flow. The small signal current can flow only through here. This is M7, and that is again from M3. All the currents remain same, which is GM into VID by 2. Now, since M3 and M4 form a current mirror and M7 and M8 form another current mirror circuit, you will see that the current on the left side will be definitely duplicated here. So the current through M4 and M8 is equal to Gm into dId by 2. Now you have come to this output point. So this is my output point. So this is the output point where this side I have the current I out marked. From top, the current coming is Gm into Vid by 2, and the current leaving this node is minus Gm into Vid by 2. That means the output current I out can be written as equal to Gm into Vid, or we can write the short circuit transconductance Gm is equal to I out by Vid is equal to Gm of either 1 or 2. Is it clear? Is this transconductance calculation clear? We have done the same thing even for the differential amplifier structure, and that could be extended even here. Can I get your response in the chat box?
Sir, can you please explain again?
Yeah, so what I have done here is, in order to find capital GM, I need to have a short circuit current IO that I marked first. That is what you are seeing here. After marking that, I looked at the differential input voltage between M1 and M2. I have applied VID as my voltage. So if VID is the voltage, I can say that VID by 2 is the voltage here and minus VID by 2 is the voltage on the other side. That is why you will get a, that is how you will get a differential voltage of VID. Now looking at the gate voltage of M1 and M2, small signal voltage, I just wrote the small signal current ID as Gm into VGS. With the same form, I wrote it as Gm into VID by 2 on both sides. Right. Now, if I write Gm VID by 2 here and minus Gm VID by 2 on the other side, M5 and M6 will carry the same current because it is the same branch. Now, on the left side, if you look at M3 and M7, Gm VID by 2 is a current flowing down. So, M3 and M7 also should have Gm VID by 2. But because of current mirror action, the same current will be replicated on the other side. And since this is grounded, I have obtained the short circuit current by this form. Maybe you can write a KCL here. The sum of currents entering is only Gm VID by 2 equal to leaving is I out minus Gm VID by 2. So with this I can write what is I out. I out will be Gm into VID, or capital Gm is equal to Gm of 1 or 2. Yeah, Amitesh, I explained now, but tell me if you have further questions, I'll clarify. How did you decide the direction of I out? So since it is short circuit current, I have just marked outside. It is anyway small signal current, right? It is not a DC current. So you can consider either way. It is a small signal current. It is not a DC current which will only have a specific direction. So depending on the signal what you have, increment or decrement, like whether it is in if the signal is increasing or decreasing, reducing, you will have both variants of that. Since this is a short circuit, this is a small signal current. Yeah, I just responded to Avinash because I saw, yeah, the same equation. Yes, you will. Any more questions? Any more questions on this? Yes, that is, yes, Avinash. Yeah, we are. It is not like we are assuming whenever we design also M3, M4, M7, M8, M5, M6, and M1, M2 all should be like those pairs should be identical. I'm not telling that the GM of all devices will be same. It is not that GM of all devices will be same. GM of each device depends on the size what we take for each transistor, but the signal current is basically coming from your input pair, right? M1 and M2. So M1 and M2 we are considering it as identical, because if you look at all the other structures, all are acting as all are providing a resistance of R0. except the current mirror load. Yeah, if you have further questions, please post. So this is GM. Similarly, how will you find R out? Let me finish that R out calculation also, and we'll come back. So R out, what we can do is, however we have done the output impedance calculation for a differential amplifier, in a similar way we can do. But since we have done that analysis once, I'm not doing it again. The only thing here is, looking down, we know that R02 will be improved by GM6 R06, and looking up, we know that R04 will be improved by GM8 R08. So keeping that in mind, I'll directly write my output impedance as GM6 R06. Okay, I'll write in this form. So previously we know that the output impedance is R02 parallel to R04. This was the output impedance initially before cascoding or before making it telescopic. But now R02 will be improved by GM6 R06, and R04 is improved by or multiplied by, R04 is multiplied by GM8 R08. So this is R out. So we can say voltage gain is equal to GM into R. In none of these cases, I didn't put the minus sign. It is understood. It is clear that magnitude, your output will be actually there will be a phase shift in the output. So AV is GM into R out. So if I write the final gain expression, I can write in this form: minus GM of 1, 2 into R02 into GM6 R06 parallel to R04 into GM8 R08. And this is just by writing only the intrinsic gain multiplication. You can elaborate this by writing it as R02 plus R06 plus GM6 R06 into R02, and similarly on the other side. That is also possible. Is that clear, or any questions on this? Now, since we have written gain, if you have questions, please post. Since we have written gain here, if I write the output swing for the same circuit, how will I write output swing? Who can help me in finding the output swing? Bharat?
Oh, yes, sir.
Yeah, Bharat, can you tell me what will be the output swing of this?
Sir, it will be VDD minus VOV of 4 minus.
Yeah, VOV of 4. I'm just writing
VOV.
because the overdrive of PMOS will be negative. That is why I'm just taking the magnitude.
Yes, sir. Then minus
VOV of 8.
8, then minus VOV of 6 and VOV of 2.
And one more is VOV of the current
source. Yes, sir.
Yeah, all right. Thank you, Bharat. Yeah, this is your output swing. All right. Yeah. So that's all. So this is telescopic op-amp, and which is single-ended. In the next class, we will look at differential telescopic op-amp. So like winding up the class for now. If you have questions, you can ask, and please do stay back.